Good day, everyone. We are reviewing Wetzel's Limnology textbook. This is edition number 4, and we are in chapter 11, which looks at oxygen distribution in rivers and lakes. And more specifically, today we'll be looking at oxygen distribution in lakes, and we are looking at subsection F, horizontal variability in oxygen distributions. So let's get started. Monitoring with high-frequency sensors has revealed that there can be substantial horizontal variability in oxygen concentration within a lake. Crawford et al. Observed a range of 75 to 95 or 94% oxygen saturation within a few meters at the surface of a North Temperate bog lake. Similarly, Van de Bogert et al. Observed large variability in oxygen concentrations on a littoral to pelagic transect in a small North Temperate lake. This spatial variability in the distribution of dissolved oxygen can occur due to multiple mechanisms: littoral plant growth, basin morphometry, inflows, and reservoir continua examined below. Littoral plants. Aquatic plants often inhabit large areas of shallow lakes and the littoral perimeter of productive deep lakes. These macrophytes attach algae and benthic mats can produce large amounts of oxygen during the day, but with high respiration at night, resulting in much larger diel swings in littoral oxygen concentration than in the pelagic zone. Sadro et al. Observed that the magnitude of diel oxygen concentration in Emerald Lake was approximately 2 times higher in the littoral zone than in the pelagic zone. Within the littoral zone, the vertical distribution of oxygen in macrophyte beds can be highly stratified, where upper macrophytes are photosynthesizing and lower macrophytes are predominantly respiring. The oxygen content of the littoral zone can periodically become severely reduced. Such is the case with large population of macrophytes senesce at the end of their growing season. Severe oxygen deficits caused by the decomposition of this organic matter can persist for several months and may extend into the open water. So before we move on to double I, let's look at this figure 1118 here. Upper, changing in dissolved oxygen in the littoral and open water areas over a diurnal period during summer in eutrophic Winona Lake. Lower, vertical stratification of oxygen within the littoral zone of Parvin Lake in a luxuriant stand of submersed macrophyte Elodia. So the first one here is the littoral and pelagic oxygen concentration on the y-axis, over time on the x-axis, over an entire day. So we have pelagic value and then we have littoral values. So littoral is along the shore, and pelagic here is an open water. And so therefore we have to assume that it's open water at the surface, or close to it. And so what we see is there's definitely more variability in the oxygen concentration in the littoral zone than there is in the pelagic zone. And that is due to the plant community living on the littoral zone and generating oxygen during the day and respiring during the night, so generating CO2 during the night. Where in the pelagic zone, in the open water area, that is not the case. You probably don't have, unless the lake is shallow. Usually if the lake is deep, or even if it's not super deep, but at least if it's not shallow, then in the open water, you don't have a lot of plants that are growing there. And so therefore you don't have a lot of variability in oxygen concentration. So here we are looking at the vertical stratification of oxygen within the littoral zone. So here we're only looking at the littoral zone, and the y-axis now is the depth, and the x-axis is the concentration of oxygen. So 0 is at the surface, and 2 meters is at depth. And Elodia is a type of aquatic plant, and apparently it starts to occur like right at 1.2 meters, if that gray zone, that's what it means. And so therefore it's not found between 1.2 and the surface. So like here we have pretty high concentration of oxygen, so in the 8 milligrams of oxygen per liter. And then we have this 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 chemical change, and in this chemocline, I guess, where we have a drastic change in oxygen over like about 1.6 to 2.5 meters. So over like 1 meter, in this population of Elodia, we have a drastic crash of oxygen, as probably because this doesn't give you time when this data was collected. So I'm assuming that it's collected during the day, and so probably at depth here at the 2.5 meter depth, we have senescing. We have like dying plants that are not producing oxygen, which is not the case right at that zone, at the 1.2 meter zone. And then here we have high oxygen, probably due to the bubbling effect of oxygen like getting to the surface. And then here we have a peak productivity at about 1.6 in terms of oxygen concentration. Okay, basin morphometry and inflows. Large horizontal variation in oxygen are found in lakes of complex basin morphometry. When a lake consists of many bays or multi-depressions, oxygen concentration can vary substantially among embayments, which may effectively function as individual lakes. For example, Muskegon Lake, a freshwater estuary of Lake Michigan, experiences summer hypoxia that is occasionally abated by the mixing of oxic water from the main basin. Similarly, Green Bay, a large semi-closed or enclosed gulf in northern Lake Michigan, exhibit a large oxygen gradient. In both of these cases, high nutrients inflows are a major driver of their horizontal variability in oxygen, which can have a large effect on littoral dynamics. Reservoirs. In reservoirs, the distribution of oxygen is highly variable, both horizontally and vertically. The complex hydrodynamics of reservoirs are unique in relation to variations in inflows, morphometry, drawdown, and outflow discharge, and other factors. As illustrated by Falling Creek Reservoir in Figure 11-20, a hypolimnetic anoxic zone often turnover. As in naturally formed lakes, the distribution of oxygen, so let's see, often develops in the summer in reservoirs, first in the Salweg of the transition zone during summer stratification, and then expands horizontally and vertically until fall turnover. As in naturally formed lakes, the distribution of oxygen and rates of loss in reservoirs are governed by a balance among mixing, inflow intrusions, photosynthesis, and losses by oxidative consumption. The processes are similar among all freshwater ecosystems, but the rates of change in reservoirs are generally much more variable and dynamic than in naturally formed lakes. Let's review Figure 11-19. Relationships of velocity and depth to sedimentation, aerial primary production of phytoplankton, hypolimnetic volume, and total dissolved oxygen, and hypolimnetic temperature in determining oxygen demand along the length of a reservoir. So this is a transect along a reservoir, and the length of a reservoir. So first we're looking at velocity. So from riverine to lacustrine, from a river to a lake. So it's high in the river. In the transition zone, it's transition to lower in the lake. Then we're looking at sedimentation and volumetric primary production. So sedimentation is low in the river and higher actually in the transition zone and lower in the lacustrine environment. And then we are looking at volumetric primary production. It's medium in the riverine environment. It gets higher in the transition zone, and then it's pretty low, or it's actually lower than in the river, in the lacustrine zone. And why it's high in the transition zone is because in transition zone, this is a shallow environment, and you have a lot of biota that are pretty good producers. You have both the invertebrates and then and then the plant, the flora, aquatic flora. So, and then in the lacustrine zone, of course, it's, I mean, assuming the lake is deep, you don't have a high productivity here. Now we're looking at depth and width, so deep and wide, and shallow and narrow. And so here we're looking at rivers, so it's shallow and narrow, transition zone, transition to a deep and wide in the lake environment. Hypolimnetic volume and total dissolved oxygen. So, so the total dissolved oxygen is low in the riverine environment, and then it's a transition zone, and it gets higher in the lacustrine zone. And then hypolimnetic temperature. So these are like both for hypolimnetic. So this is for the bottom of that lake. And the temperature is high in the riverine environment, where it's low in the lacustrine environment. In terms of oxygen demand, where oxygen is in demand, pretty much, as the title might be, it's low in the riverine environment because you have very oxygenated water because of the turbulence. And it gets higher in the transition zone, in the shallow area, and then it's low again in the lacustrine zone. It's actually, it appears a little lower than even the environment of a river. Okay, so let's look at figure 11-20 here. Dissolved oxygen concentration measured at 5 sites on a longitudinal transect in Falling Creek reservoirs from the inflow tributary to the dam on 4 selected dates. So April, June, September, and October. So this is at 5 sites. And so the 5 sites are like 1, 2, 3, 4, and 5. So those are the horizontal lines of the site. So we're looking at the cross-section of that lake. And then A is April. So across that lake in April, this is the oxygen concentration and distant from inflow. So the oxygen concentration is color-coded. So it's high when it's in the blues, and it's low when it's in the reds. And then the green is the transition kind of concentration in between 6 and 9 milligrams per liter. And so then this is the bottom of the lake, and so this is dirt, sediment, and then this is the open water. So what we see in April is we see pretty high concentration throughout the lake, except for the hypolimnion, for the one that really is in contact with the sediment, and then also except for the shallow zone. In June, we have a chemocline here. We have a change in concentration of oxygen throughout the lake, and we still have a remaining very high concentration, and actually higher concentration in the metalimnion, and that is probably due to the production of oxygen from the plant, from the algal biomass, as well as the microbiota. And then we have very low concentration here in anoxic environment or close to it at the sediment. And then we have this sort of like pocket of higher dissolved oxygen right here. Then we're moving on to September. So September is it doesn't say if it's. I mean, this is a reservoir. So, and so like this is the inflow, and then this is the outflow of the reservoir. So this is the dam. So we still have that strong tongue of anoxic water persisting here, but in the metalimnion. And then we have still a little bit of oxygen persisting as well, and getting really, very close. So the high concentration are around the dam, and because then we have better distribution in the riverine environment. And then lastly, this is in October. So in October, we have pretty uniform oxygen concentration for the entire lake. And there's a little bit higher here. I'm not sure why we produce oxygen right here at the interface, or maybe it's just a remaining value here. You can see there's a pocket there, and which doesn't appear to be the case. The pocket disappears in September, but then it reappears here. I'm not sure what that production, and maybe it's the mixing that is generated by the outflow of water from the dam. And but yeah, I mean, it's pretty surprising. And then ultimately, you're going to end up having this type of distribution in April. So changes in lake oxygen concentration at decadal and continental scales. Human activities are altering large oxygen concentrations at large temporal and spatial scales. In North America and Europe, monitoring data from 393 lakes show a median decrease in bottom water oxygen concentration of 0.12 milligrams of oxygen per liter per decade, attributed to strengthening thermal stratification and decreasing water quality. Surface water oxygen concentration were not variable, while some lakes exhibited decreases due to warmer temperatures, others increased due to greater productivity. Paleolimnological records from 365 lakes support an increasing incidence of hypolimnetic anoxia over the past century due to nutrient inputs. Importantly, this study also revealed the lack of recovery to well-oxygenated conditions in lakes that had multiple decades of nutrient abatement. In synthesis, global change, namely climate change and eutrophication, may decrease apolimnetic oxygen concentration in some lakes at the decadal scale, while at shorter time scales, lake oxygen may potentially be more variable. For example, 41 years of monitoring data of Belham Tarn in the UK showed that the duration of hypolimnetic anoxia significantly increased over time, but year-to-year hypolimnetic oxygen depletion was associated with spring wind and chlorophyll A levels. Similarly, a 44-year analysis of Sal reservoirs in Spain by Marseille observed greater anoxia over time due to declining inflows, with year-to-year variability in oxygen related to El Niño southern oscillation periodicity. In contrast, Lake Tovel in Italy exhibited higher deep water oxygen concentration over 8 decades, as decreasing ice cover has resulted in longer mixing period and greater replenishment of hypolimnetic oxygen. Collectively, these three studies underscored that different global change drivers will interact at a range of spatial and temporal scales to affect lake oxygen. 5. Metrics for assessing anoxia and hypoxia in inland waters. When processes consuming oxygen exceed processes supplying it, oxygen concentration may decrease below an unacceptable threshold. For example, the minimum oxygen level needed for fish survival. A condition called hypoxia, the threshold for hypoxia is variable, but usually set between 2 and 6 milligrams of oxygen per liter. If oxygen concentration decreases even further, anoxia develops, with threshold usually set between 0.5 and 2 milligrams of oxygen per liter. Anoxia is closely associated with the redox condition at which anaerobic metabolic pathways occur, because most anaerobic metabolism are inhibited by oxygen concentration above 2 milligrams of oxygen per liter. Anoxia and hypoxia are among the most active environmental problems facing inland waters, as their prevalence are rapidly increased and likely will become even more frequent in the future. Appropriate metrics to assess anoxic and hypoxic conditions are thus fundamental for managing inland waters. Beyond metrics-based oxygen concentrations, there are two major approaches for assessing oxygen deficits in fresh water. Rate-based metrics focus on the velocity of oxygen consumption in a water parcel, with extent-based metrics focus on aggregated estimates of the spatial and temporal extent of anoxia or hypoxia. Here, and we'll pick it up tomorrow at rate-based metrics. And that's about it for today. And I thank you for your attention, and I'll see you tomorrow. Bye.